Welcome to the lecture number 3. From this lecture, we are going to start with the basic fundamentals of linear regression modeling. We are essentially going to start with the chapter Simple Linear Regression or Simple Linear Regression Analysis. Well, in practice, the contents of this chapter or the basic concept which we are going to learn in this chapter may not really be helpful. A more important chapter will be next chapter, that will be multiple linear regression analysis, but whatever concept we are going to learn here, they are going to build up the basic fundamental for the next chapter. The difference between simple linear regression analysis and multiple linear regression analysis is that in the case of simple linear regression, we are going to consider only one input variable, whereas in the case of multiple linear regression analysis, we are going to consider more than one input variables. And in practice, we know that any output is dependent on more than one input variables. So, that will be a more realistic chapter, but whatever the concepts we are going to discuss in the case of multiple linear regression model, they are based on the concept that we are going to learn in this simple linear regression model. And as an instructor, it is also easy for me to explain the things when there is one variable, and I can use this one dimension, two dimension graphics, and later on I can simply extend it to a multiple case. Right. So, okay. So, here we are going to consider a situation where we consider only one input variable. Right. So, now we consider that the output variable here y, that is linearly related by this function beta 0 plus beta 1 x. So, now you can see here, this is the same model that we had discussed in case of lecture number 1 and lecture number 2. Okay. So, in this case, just for your information, this is your here so called output variable. This is how we had denoted it earlier, and this was we had called earlier in the elementary language as input variable. Now, we are going to talk about the pure statistics language, right. Okay. In pure statistics language, this y and x, they have got different names. For example, this y is called as steady variable, and in connection with steady variable, this x is called as explanatory variable, right. And this has got several other names also. For example, this y is also called as response variable, and when we talk of response variable, then we talk of x as regressors, or say sometime regressor variables and so on. And this is also called as dependent variable. Okay, y is called as dependent variable, and in connection with dependent variable, I can call this x as independent variable. So, similarly, there are some other names also that are popular in the literature, right. But these are some common names that we try to use for this here y and x. And just for your remembrance, this beta 0 we had taken. This was our interceptor, and this beta 1 was the slope parameter. If you try to recall, in the lecture number 2, we had considered the linear equation y equal to mx plus c, and which I had translated in terms of y is equal to beta 0 plus beta 1 x, right. Okay. So, now this is my model. The question is that how to know this model. We had discussed earlier that model is nothing but a function between the output and input variable. And when I say I want to find out the model, that is equivalent to saying that I want to find out the parameters of the model. Right. So, here once I say that I want to know the model, our objective is to know or find the parameters. Well, up to now we have defined here two parameters, one is beta 0 and say another is beta 1. Well, there can be some other parameters also that we will see later on as we move further. Okay. Now, we are discussing here the technique of regression analysis. We had discussed that regression means to move in the backward direction. So, what are we going to do here, that we are going to conduct an experiment, or we are going to observe some data in some real life experiments, and finally we will have a sample of data. Now, I have to find out the values of the parameter, or equivalently I want to find out the model using this data. So, let us try to start with this thing, right. Suppose I say that now we are going to conduct an experiment and obtain data. Well, we are going to find some finite number of data, right. So, let us say we want to obtain n data sets. What does this mean? That means we are going to conduct the experiment and record the data n times. This means what? For example, if I consider the same example that we considered earlier, that y is the yield of a crop and x is the quantity of fertilizer, then for example, I can take here that x1 that is equal to 1 kg of fertilizer, and I give it to the field, and then I try to observe how much yield I get after some time. So, suppose I get the yield y1 is equal to, suppose here 20 kilogram. Then the next time I try to take here 2 kg of fertilizer, and this will be my here the value of x2. And suppose I get here, suppose 30 kg of outcome, 30 kg of yield. So, this is going to be my y2, and so on. I try to repeat it n times. So, what will happen? At the end I will have a data something like x1 y1, x2 y2, and so on, say xn yn. So, this is my here observed data set, right. Now, what is your objective? Your objective is that using this data set, I have to find out the value of the parameters of my model, and that would be nothing but finding out a model, right. Okay. Now, the next question is how to start it. Well, we have assumed that there is a linear model between y and x, right, that we have to keep in mind, because we are going to consider here only the linear regression modeling. Okay. So, the first step is that I can plot this data on a two-dimensional plot, something like this. This is my here x axis, this is my here y axis, and suppose I plot the data and say x1 y1, say x2 y2, x3 y3, x4 y4, x5 y5, x5 6, and so on. Now, one can see from this graph that the points are following a sort of linear trend, right. And one can see here that if somebody tries, there is a trend like this one, right. But this is only a trend, and now if I assume that this is my model for a while, then I would like to know what is the equation of this line, right. So, in case if you try to see, let me mark here these values here, something like this is my here x1 y1, this is my here x2 y2 and so on. Right. On the other hand, it is not always necessary that the trend between x and y is always increasing. In fact, means there can be other possibility also that the observations are lying like this one. So, once you get the data, try to plot it and then try to see the trend in the data. In case if the trend in the data is linear, that gives us first assurance, yes, a linear model can be fitted to the given data set. Or in simple words, I can assume, yes, the process can be described by a linear equation. Well, okay. So, now if you try to see, I simply assume that there is a model. The model is now going to be something like y is equal to beta 0 plus beta 1 x. This is the model that we have considered, right. So, now I believe that whatever observations I have obtained here x1, y1, x2, y2 and say here this xn, yn, they are actually going to follow this model, and these observations are generated from this model. This means that each set of observation will satisfy this equation, beta 0 plus beta 1 x I goes from 1 to n. But if you try to observe this graphic, this two-dimensional plot, is it really happening? No. If I try to write down, this orange line is something like y is equal to beta 0 plus beta 1 x. And we are assuming that whatever are my points here, they are lying on this line. So, essentially what we are assuming that this point is going to lie somewhere here, this point is going to lie somewhere here, this point is going to lie somewhere here, and well, this point is lying on the line and so on, right. But now you can see that this model is not appropriate because that is not really describing the true phenomena. The observation which I have got here x1, y1, x2, y2, x and yn, they are indicating, yes, the approximate relationship is here yi is equal to beta 0 plus this beta 1 xi, but this is not exact. So, I can do one thing, in order to make this model more realistic, I can add here a term. For example, I can rewrite it yi is equal to beta 0 plus beta 1 xi and plus some random error epsilon I. I goes from 1 to say here n. What is this epsilon I? Epsilon I is the random error involved in the ith set of data, random error. So, when I observe the ith set of observation xi, yi, this has got some error epsilon I. So, I can assume here, for example, in the case of this here first observation x1, y1, I can write that okay, this difference whatever is going to be here, this is trying to denote something like epsilon 1. And similarly, when I try to go for this x2, y2, this difference is going to be something like epsilon 2 and so on. So, in some cases you can see here that this epsilon 1, this distance, this is the distance of x1, y1 from this line that we want to know, that we want to fit. And this point x1, y1 is lying above the line. Whereas, if you try to see in the case of x2, y2, this epsilon 2 is the difference between x2, y2 and this line that we want to fit. And this observation is lying under the line. And the same thing is happening with all other points. So, I can say that some random errors are in the upward direction of the line, and some random errors they are under the line. So, I can assume that here that epsilon I has to be a random quantity which takes some value that can be positive or that can be negative. Right. Okay. So, now I call this thing as a linear regression model. And if you try to see what is the difference between this model and this model. Now, if I say what is the difference between these two models, so if you try to see, this was a sort of exact relationship, but this is going to depict a statistical relationship. This means what? I am not saying that all my observations are exactly going to follow the straight line, but they are very close to the straight line, and there are certain random errors which are deviating the observations from the main line. So, now I can see here that this orange line is going to depict the line that we want to fit on the basis of this given set of data, say x1, y1, x2, y2, xn, yn. And now our objective is this, how should I find this line? But before that, we have to make some assumption for this random error. Right. Okay. So, what we try to do here, so we are going to assume here that the mean of epsilon i's is 0. Right. And in statistical language, I can write down here, say expected value of epsilon I is equal to 0 for all I goes from 1 to n. Well, if you do not know the meaning of this E, I can just explain you before I move further. E is the expectation operator, right? And we define it in the following way. If I say if there is a random variable, see here some random variable here z, which is going to follow a probability density function, say fz with parameter theta, right? This is my here probability density function, and where z is the random variable and theta is the parameter. Then we try to define, say, expected value of z integral over the range of z, say here z fz dz, right? And in case if you are using a discrete random variable, then in place of the probability density function, we try to use the probability mass function, and this integral is replaced by the summation. Right. Similarly, at the same point, I can also tell you that how do we define the variance. We will denote it by here VAR, variance of z. This is defined as expected value of z minus expected value of z whole square. So, this is nothing but integral of z minus expected value of z whole square fz dz, and the integral is over the range of random variable z. So, this is how we try to define this expectation and variance. So, now I can make here two assumptions as I wrote here, expected value of epsilon I to be 0 and variance of epsilon I to be sigma square. What does this mean? Once I write that expected value of epsilon I is equal to 0, that means we are trying to say that the mean of epsilon I is 0. This means that some observations they have got a random error which is positive, and some observation they have got random error which is negative. and once you try to find out its arithmetic mean, their average value is going to be 0. And that is expected also from the application point of view, that in a realistic experiment, sometimes the errors are positive and sometimes the errors are negative. So, it is reasonable to assume that the average of those errors is going to be 0, right. And but it is a random variable, epsilon I is a random variable. So, so we need to describe its behavior by its variance also. For example, if you try to see in this figure also, these epsilons I sometimes they are lying in the upward direction, sometimes they are lying in the downward correction, and moreover every observation will have a different type of random error, different amount of random error. So, that is described by the quantity of sigma square, right. So, in simple words, if I say if the sigma square is low, then I would say that my observations have got less variance and they are lying more close to the line. And in case if my this sigma square is high, then I would say that my observation have got more scatteredness and observations are lying quite away from the line, right. Okay. So, now at this moment, now if I try to consider this model, that y is equal to beta 0 plus beta 1 x plus here epsilon. So, you can see here that I have assumed this to be random, right. Now, we also assume something about y and x, and let us see what is their behavior. So, we assume here that this x is also non-stochastic. Non-stochastic means it is non-random in simple language, right. In practice, there can be situation where x can be random also, but here in this course we are going to assume that x will remain as fixed, right. Similarly, going on the same concept, I also assume that beta 0 and beta 1, they are my parameters, and this I will say that they are fixed but unknown. Right. In some cases, this beta 0 and beta 1 can also be random, but we are not going to consider those situations in this course. Okay. So, now since epsilon is random, beta 0, beta 1 and say x, they are not random. So, this y also becomes random. So, after this, if you try to see, we also have assumed that this expected value of epsilon is 0 and variance of epsilon is sigma square. So, that means if I want to know my complete model, I also need to know the value of sigma square. So, the sigma square also become a parameter of the model. So, now you can see here that we have got here 3 parameters, beta 0, beta 1 and sigma square. So, once I say that I want to know my model, that is equivalent to saying that I want to find out the values of beta 0, beta 1 and sigma square. And how to find them? Just on the basis of sample of data x1, y1, x2, y2, xn, yn. We also assume here that when we observe the observations x1, y1, x2, y2, xn, yn, then the corresponding random errors epsilon 1, epsilon 2, epsilon n, they are IIDs. IIDs means they are identically distributed as well as they are independently distributed. So, all epsilon 1, epsilon 2, epsilon n, they are mutually independent of each other, and all epsilon 1, epsilon 2, epsilon n, they are coming from the same distribution. Now, let us try to understand what is the interpretation of beta 0 and beta 1 of beta 0 and beta 1. So, if you try to look at this model, y is equal to beta 0 plus beta 1 x plus epsilon, we had assumed that expected value of epsilon is equal to 0. So, I can write expected value of beta of y is equal to beta 0 plus beta 1 x, right. So, now if I say x is equal to 0, that means independent variable takes the value 0, then expected value of y is equal to beta 0. And if I try to find out the first derivative of expected value of y with respect to x, then this comes out to be beta 1. So, now this beta 0 and beta 1 have some interpretation. Beta 0 is the average value of y or average value of a response when independent variable takes value 0, and beta 1 is the rate of change in the average response, average value of response when there is a unit change in the value of independent variable x. So, this is how we try to interpret the values of beta 0 and beta 1 in case of linear regression modeling. So, beta 0 is simply the average value of y when x takes value 0, and beta 1 is the slope of the line which is measured by the first derivative of average value of y with respect to x. Okay, so now we stop here, and in the next lecture I would explain you how to estimate these parameters using two techniques. One is ordinary least square estimation and another is maximum likelihood estimation, right. Till then, goodbye.